Hi, class, welcome. Today we're going to do a brief overview of various parts from Chapter 2, Ultrasound Sound We Don't Hear. At this point, you should already know that sound is a traveling variation in acoustic variable. That is, as sound travels through tissue, it's going to cause a change in acoustic variables. And the acoustic variables are pressure, density, particle motion, distance, or vibration. As sound travels through the body and these various factors change, so that means pressure changes, density changes, and there is particle motion or a change in particle distance. If we focus for a moment on just the pressure alone, okay, so the very top, these peaks represent the areas of the sound wave that are high pressure, high density. The bottom parts here are the troughs, and these represent in a sound wave, they represent the areas of low pressure, density, and particle motion. If we focus on just this top half, right, where pressure is high and density is high, but for a moment, when we're talking about a new topic, which is tissue harmonics, you kind of have to forget about the density and you kind of have to forget about this because the only thing that really matters when we're talking about harmonics is pressure. Okay, so to connect some of these dots, initially you learned what sound is, and you learn that sound is a traveling variation in pressure density or particle motion. And those three together are part of a group called acoustic variables. They are part of this group called acoustic variables because these are variables or quantities that change within a sound wave. But I'm trying to introduce you to the next topic, which is harmonics. And in this book, harmonics, you're in the physics book. You're going to learn about three types of harmonics. You're going to learn about tissue harmonics, harmonic imaging, which is called pulse inversion harmonics, and you're also going to learn about contrast agent harmonics. Right now, I'm introducing you to the first type of harmonics, and that is tissue harmonics. And so that is located on page 19 in your book. So if we focus on just the word pressure for a moment and we don't try to tie in density or particle motion, just pressure, we know that as a sound wave travels through our body, it's going to create areas of high pressure and low pressure. Well, we need to know how the sound wave responds differently during high pressure and during low pressure. So, when the sound wave first comes out of the transducer, it starts passing through your tissue just like this, right? This is what we're used to seeing when we're trying to envision sound waves in chapter 2. If we focus on just the high pressure regions, which are the peaks or the areas of compression, the sound wave is going to travel faster during those portions. So when I think of moving faster, I kind of think that each one of these sound waves is kind of being pushed forward or like pulled, um, changing the shape of the sound wave, right? So if the sound wave is traveling through the tissue, it's now going to go faster during compression, high pressure, and then it slows down during rarefaction, and then it goes faster during high pressure portions, and then slower during rarefaction, and then high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. And you can see how the sound wave has changed its appearance. So initially, the sound wave was called sinusoidal. And now they call it non-sinusoidal. Okay. And the non-sinusoidal represents the sound wave traveling faster during high pressure portions of the wave, if we could magically see it. Okay. So we need to know that this is what the sound wave does. It will travel faster during high pressure portions of your body. It's not something that you can control at all, or your machine cannot control this. This is something that happens because when the sound wave is introduced to your body, remember your body is going to respond with high pressure, low pressure, high pressure, low pressure. And so this is just kind of like what happens. The sound wave travels faster during high pressure portions of the sound wave. And so the other part of this that you need to know, so there's a couple other things. If the sound wave is traveling at the same speed, so this represents a sound wave that's traveling at the same speed, regardless if it's going through an area of high pressure or low pressure, it's traveling at the same speed. This represents a sound wave where it's going faster and then slower and then faster and slower. So the fact that the sound wave is traveling at different speeds, inconsistent speeds versus like the same speed, they describe that, physics describes that as non-linear behavior. So linear behavior is some like traveling at the same speed, 65 miles per hour from here to Las Vegas. But if you're gonna, drive faster during like no traffic areas and then slower during low traffic areas. But instead, now you can say, well, I guess that doesn't make sense. But anyway, the fact that you're traveling at different speeds, um, you would be described as having a non-linear propagation, not consistent. They also call it non-linear behavior. But anyway, this non-linear behavior actually has a positive effect on the sound wave. It has a positive effect on the image. So when the sound wave goes from sinusoidal to non-sinusoidal, the original frequency of the image is doubled. So if you originally had a transducer that said that was like a 2 megahertz transducer, right? And that's what you're like scanning, that's what you're using. Well, because the sound wave that's coming out of this 2 megahertz transducer moves from sinusoidal to non-sinusoidal, this original frequency is doubled. That's kind of like the rule of thumb. Whenever you hear in physics, whenever you hear the words non-linear behavior, non-linear propagation, as is associated with this non-sinusoidal sound wave. So whenever you hear that, those non-linear words, then I want you guys to connect it to a change in frequency. So this was the original frequency. The change in frequency is always going to be doubled. So like if the original frequency was a 2, the new frequency, which is called the harmonic frequency, is going to be doubled to a 4. So as you can see, this is an even number. So they call it even harmonics. If you were using, like, let's say a 7.5, that was your original frequency. Well, again, it would have been doubled to a 15. This is an odd number. So sometimes they call it odd harmonics. So it doesn't really matter if the number is odd or even. That's not the takeaway here. The takeaway is just to know that the original frequency doubles. The original frequencies the original frequency has a lot of AKAs, and we use the mnemonic rune fee. This is what I do in my class. If you don't like it, you can come up with something else. But this stands for original operating, natural, fundamental, and emitted. He doesn't start using emitted till a little bit later in the book. Okay, so these are all AKAs for the original, and I just usually remember it by rune fee. The new frequency is not going to be called room free. It's going to be called even and odd harmonics, harmonic harmonics, tissue harmonics. In some way, shape, or form, it's going to be called harmonics. And you always have to know that rule of like the frequency always doubles. And this is some information here on harmonics and how it is affected by the high pressure portions of a wave. Here's some more information about harmonics. I really like this picture. So when I think about harmonics, I have to definitely take it to the idea of pressure. So early in chapter 2, they introduced the word pressure to you, and then piggybacking off of pressure is knowing what tissue harmonics is, right? It's because high pressure regions are where the sound wave travels faster, and like the fact that the sound wave travels faster is why the frequency doubles and it has actually a positive effect on your image. Here's an example of image A and image B. Image B is made with harmonics. And as you can see, it says that it contains more detail or spatial resolution. If you think back at what you know about frequency, the higher the frequency we use, the more detailed our image is. And so the image does look a lot cleaner and more appealing than it does in image A. As I mentioned a moment ago, I do like this image of this sound wave. This is like more realistic to like how the sound waves in chapter 3 are going to be discussed. They're not going to be discussed as like squiggly, wavy lines. But what I like about this image is I like the vibrancy of the red, and I just kind of remember where it's located. Notice how it's located along the beam's main axis, which means like the central point of the beam. That's one of the things that you want to remember. That's number 4 here. Number 3, we've already talked about. Number 2, when we talk about harmonics being created during transmission. Well, the whole idea of harmonics is like the sound wave passing through the body and it travels faster through high pressure portions of the body or like the sound wave, correct? So we're talking about the sound wave. We're not talking about the echoes. So the fact that we're talking about the sound wave, it is the sound wave that transmits in the body. The echoes would be called the reception portion, right? So pulses are transmitted. So during transmission, right? So anytime we're talking about pulses, we're talking about transmission. The sound wave is being transmitted through the body, whereas echoes would be the reception or the receiving part, right? The transducer is transmitting a pulse, but it is receiving an echo. So this whole story of harmonics, we're talking about harmonics being created along the beam's main axis, the pulse's main axis. So not the echo, obviously that's why it's functioning through transmission. And then number 1, I also like this picture because it really does help me understand number 1 or remember number 1. You notice that the red, which represents that harmonic frequency or like that harmonic energy, starts a little bit deeper. It doesn't start as the sound wave leaves the transducer. It occurs later. So it'd be later in the sound wave, which would also equate to like a sound wave that's like later in the tissue, like further or deeper. So harmonics is not created at very superficial depths. It is created deeper within tissue, as it is like represented in this image, right? It harmonics kind of starts right around this level, which is like deeper within the sound wave, which would represent deeper within the tissue as well. Okay. But this picture really does it, and the more you study it, the more it will make sense. Okay, so that kind of wraps up my overview of harmonics or AKA tissue harmonics on page 19. And then I would like to also discuss incidence, which we're going to talk about 2 types of incidences today, the 2 that are outlined in your book, and those start on page 30, and it's perpendicular incidence and oblique incidence. So those are 2 types of incidences that we're going to talk about. Well, what is an incidence? An incidence is whenever we say the word incidence in physics, we're talking about the sound wave. that comes out of the transducer. So we're talking, so if this is the transducer right here, this sound wave that's coming out of the transducer, instead of just calling it, the sound wave, we're going to call it the incident sound. So think about it as an AKA, or we can call it the incident angle. Okay, and the sound wave, or the part of the sound wave that continues to propagate deeper and deeper and deeper, which is this part, is going to now be referred to as the transmission angle or the transmission sound. And this is the tissue that goes deeper and deeper into the second medium. So as you can see down at the bottom of the picture, it says medium one and medium two. The sound that reflects back to the transducer is going to be called the reflected sound or the reflected angle, as we've already been calling it. And so that's the sound that reflects back into the medium one. Okay, so now that we know those three definitions, we're going to turn our attention specifically to perpendicular incidence. Perpendicular incidence has a lot of AKAs. The AKAs that you guys need to remember for perpendicular incidence are perpendicular, orthogonal, right, normal, 90 degrees, and in our testing at the campus, often referred to as 0 degrees, which is what it is in geography. Okay, so when we're talking about perpendicular incidence, and in this book it's called perpendicular. In other physics books, it's often referred to as normal. Those are probably like the two more common AKAs, but you definitely should know them all. When we're talking about the perpendicular incidence, you have to envision that the transducer is located right here, okay? So the sound that comes out of the transducer is represented by this dark purple, and this is the incident sound. And this is the sound that is going completely perpendicular. That's why it's called perpendicular incidence, completely perpendicular to this boundary right here. So here's the boundary in green, and then this is the sound wave coming out of my transducer. And as you can see, those are completely perpendicular. Okay. And then when we're talking about the reflected, notice what the reflected is doing. The reflected is going back towards the transducer. So if you look at if you look at these two arrows, right, these two here, you can see that they're described as going in an opposite direction, but along the same path, right, as the incidence. So the reflected pulse is described as being the opposite direction of the incident, but along the same path. The transmitted is going the same direction as the incident. So I'm now comparing this one here and this one here. The transmitted pulse here in medium two is represented, is described as going the same direction as the incident and again along the same path, right? Like they'd be going. So as you can see, everything is like along like this really nice straight line. Everything seems very organized. Now, normally here, you would expect to see medium one, right, and medium two. But instead of medium one and medium two, they have a Z1 and a Z2. And that's because of the units associated with perpendicular incidence. Perpendicular incidence describes how much of the original intensity is going to be reflected and how much of the original intensity is going to be transmitted into medium two. So the pulse has a 100% intensity when it leaves the transducer. So the incident pulse or the incident angle is at 100% or at 1. So if this is at 100%, the transmitted and the reflected, when these two are added together, they must equal the incidence. So the reflected pulse plus the transmitted pulse must equal the incidence. This plus this must equal 100% or 1. So if I say that most of the pulse was reflected at the boundary, then you could assume that the transmission pulse was very small, right? Because for example, if I say most of the pulse was reflected, so 80% was reflected, then that only needs 20% to be transmitted. or we could say that, 90% was transmitted, and then that only leaves 10% to be reflected. An important idea about this that they like to ask on the SPI is they like to ask you about this boundary. That what you want to know is the conservation of energy at the boundary. And that's just a rule that describes I guess there must have been a question at some point, right, where it's like, okay, so this is the incidence is at 100% intensity, but is any of the intensity lost at the boundary, right? So like an example of that look like it is this, right? If I said the incidence was at 100%, and then the transmitted was 70%, and this is 20%. Okay, we'll do the math here. If I add my 20% plus my 70%, that's only 90%, right? And we know that it has to add up to 100. So the question was, does some of the intensity get lost at the boundary? Like merely for the fact that the sound wave is passing through a boundary into a second tissue. Is any of that energy lost at the tissue interface or the tissue boundary? And the answer is no. And that is known as no energy lost at the boundary between two tissues. No intensity lost at the boundary between two tissues. And therefore, it's described as the conservation of energy. So that's something that you should know. Um, and so now, as I mentioned a moment ago, there's a Z1 and a Z2. So this goes back to what I was mentioning about the intensity, right? So we know the incidence is 100%, and we know that these two added together must equal the incidence. And so, like, what's going to be bigger? In this picture, like, looking at these two arrows here, the reflected arrow is really small and the transmitted is really big. So just from this picture alone, I'm going to say, okay, well, there's a bigger intensity that was transmitted and a smaller intensity that was reflected. But actually, that's not always the case. This is just one way of drawing the picture, but they could have made a smaller transmission and they could have made a bigger reflected. So, like, now the question is, like, what's bigger? Well, what's bigger, right? Is the reflected intensity bigger or is the transmitted intensity bigger? Depends on tissue impedance. Tissue impedance is also another way of thinking about impedance is resistance. And that is represented by by the letter Z, which represents the unit of rails. Okay, so this represents how those three arrows that we just looked at a moment, how they're described. But if you look at this last bullet, it says the intensities of the reflected and the transmitted depends on the tissue impedance, aka tissue resistance. And that is outlined on page 31. Impedance determines how much of the incident sound is reflected and how much is transmitted into the second medium. You should know that impedance is equal to the density of the medium multiplied by the propagation speed. A common question that you might see is what determines tissue impedance? What makes a tissue more resistive and one other tissue less resistive? What has to do with the density of that tissue? And so is the tissue going to be more dense? If it is going to be more dense, it's going to have a higher resistance. If the tissue is going to be less dense, it's going to have a lower resistance or a lower impedance. The average soft tissue impedance is 1,630,000. That's a really important number to write down on your numbers list. So now that we know what impedance is, it has to do with the density and the propagation speed. And we also know that impedance is also described as being resistance, a tissue's resistance to the sound wave. Um, so now we have to talk about three different scenarios of impedance, okay? So if the tissue 1 and the tissue 2 has equal impedances, then you have to know that there's no reflection, right? 0% reflection leads, must only mean that 100% of the sound wave is transmitted. Because remember, the reflected plus the transmitted together has to equal 100. So if there is 0% reflection, there must be 100% transmission. Okay, the second scenario that you should know is what happens when there is a little bit of a difference, so a little difference in impedance. Well, if there's a small difference in impedance, then you're going to have a larger transmission and a smaller reflection. Okay. And then in the case of vastly different impedances, you're going to have I'm sorry, you're going to have a very large reflection and the opposite, a very small transmission. And this last scenario is one that is especially important. You have to know what is larger? Is it the reflection or the transmitted? And they don't always call it reflection and transmitted, as you've learned from the lecture, that they also refer to it as the intensity reflection coefficient or the intensity transmitted coefficient, so ITC or IRC. Instead of just saying transmission or reflection, they might just make it a little bit more fancy on you, and that's okay. And so, um, it has to do with tissue impedance, and you have to know all three scenarios, but one scenario, this idea of vastly different impedances, right? So say it with me. Vastly different impedances always result in large reflections, which means small transmissions, right? That is a rule. You should write that down. It's something that you're going to hear over and over in physics a few more times, and you're going to get questions on that. So you kind of want to remember that one. These are all important, but that one kind of pops up a little bit more often. Okay, while we're talking about vastly different impedances, I want to take a second to explain the reason we use gel, which is also called a coupling medium in physics. Well, even if you press the transducer up against the skin, so here's the transducer and here's the skin. There's going to be itty bitty little microscopic air bubbles that are kind of wedged in between the transducer and the skin. These air bubbles have one type of impedance, and then your skin has another type of impedance. And when compared, these two have a vastly different impedance. And as I mentioned before, vastly different impedances equal very large reflections and small transmissions. Okay, so what does that actually mean? Still, how do we connect that to the gel we use? Well, when the sound wave is coming out of the transducer and it wants to propagate deeper in tissue, it has to follow that rule. It realizes that the air impedance or resistance is very or density, I could say, is very different than the density or impedance or resistance of the skin. And so instead of a lot of the sound wave wanting to go deeper and deeper within tissue, actually the opposite. A little bit goes into the tissue, so a small transmission, but most of it reflects back to the transducer. And so there just isn't enough sound wave transmitting. And that is exactly why if you don't use gel, you kind of get a little bit of layers of tissue up here and you get no more image because there just wasn't enough sound wave to propagate deeper and deeper. Too much of the sound wave reflected and not enough transmitted. So that's the actual reason, or one of the reasons we use gel. But again, there's the second time the book has mentioned vastly different impedances. Okay, so now let's talk about our second type of incidence, which is oblique incidence. Luckily, oblique doesn't have a lot of the AKAs. It's just referred to as oblique or non-perpendicular or like non-normal. Literally any of the non-orthogonal, right, normal, whatever, just put a non in front of it, and those are the AKAs. So for this one's described very different. And so please do not cross the information over. So what I just taught you about perpendicular, box that up, tape it up for a little bit. You're going to visit that later when you study, but oblique is, a completely different brain box, and I don't want you to mix the two up. So when you're talking about oblique incidence, you're going to focus here on this angle. This is the angle I didn't want it like that. This is the incident sound. It is called oblique because as you can see, it is going oblique to the boundary. And if you don't know, if you didn't know where the boundary is, this pink is the boundary. And you can see that the tissues are one's in light gray, one's in darker gray to represent two different tissues. So if you look at this sound wave, it is traveling in a direction that is oblique to the tissue interface or the boundary between two media. The sound wave that is reflected, as you can see, it is going in a different direction. That sound wave is described, or that reflection is described as not returning to the transducer, and you can see that from the picture. It's described as being equal but opposite of the incidence. Equal but opposite. Opposite because it's literally the opposite angle of if you're comparing these two lines here, these are opposite of each other. But also, if you draw an imaginary dotted line between these two, okay, and you measured from the dotted line to the incident angle and from the dotted line to the reflected angle, these measurements would be the same, would be equal. And that's why they say equal but opposite. Okay. Now, that's really all it says about the reflected. It says that it's, the reflected sound is going through medium one. It's not returning to the transducer. It's going equal and opposite to the incident. And that's really all they say about the incident, about the reflected. The transmitted angle, though, now let's focus our attention here. You can see that here's a dotted line, and that could be it says expected transmitted angle. And this is the transmitted angle. And so this is what was expected, but this is what it really is. Okay, so if I look at what I expected the transmitted angle to look like, I guess, yeah, I did expect it to go in the exact same direction as the yellow, which is the incidence. And this would have happened. There would have been no change from the incident angle to the transmitted angle, right? So these two would have been equal. The incident angle would have been equal to the transmitted angle. They would have been the same if there was the same propagation speed in medium one and medium two. So if the prop speeds in medium one and two are equal, then there would have been no change between the incident sound and the transmitted sound. There would have been no change in angle, right? So if they said like the incident angle was, I don't know, 45, then this would have been 45 as well, okay? But if the sound wave, the transmitted angle changes direction, right? So sometimes when it changes direction, they call it refract. Okay. So this example here, refracted. And what does that mean? It just means that it changed directions from the incident, right? So if we're drawing the incidents like this and then it refracts down like that, you could see how like the angles are different, right? So there was this right here, there was a bend, right? That bend in transmission is called refraction. And so, why did that happen? Why did the sound wave refract? The sound wave refracted because there was actually different propagation speeds in the tissue. So, tissue one, the light gray, had one prop speed, tissue two, the darker gray, had a second prop speed. And so, when there is different propagation speeds, plus, not either or, but plus oblique incidence, this guy coming obliquely to the boundary. So you have those two things. Okay, hold on. You already know what I'm going to do, right? So I have the oblique incidence, check. I have the different prop speeds, right? We're going to pretend these are different prop speeds, check. Okay. So if I have that, look what happens here. My sound wave refracted. It bent during transmission. And this has a negative effect on your image. This will distort and duplicate the image. So, or like a portion of the image. So, for example, here's the aorta, and then it'll be doubled. And as you can see, the duplication, right? The doubling is side by side, which is called lateral duplication. Later, when you guys learn about lateral resolution, you're going to realize that this has a negative effect on your image, like obviously, right? Because it's an artifact, it's a mistake, it's an error in imaging. Whenever the screen does not accurately represent your body, it's called an artifact, which is an error in imaging. So if the screen doesn't represent your body in like any way, shape, or form, like in your body, you have one structure on the screen, you have two. In your body, you have something on the screen, it's missing. In your body, you have something deep on the screen, it's superficial, or the other way around. If you have something small in your body, it looks big on your screen, or the opposite, anything. If it's wrong in any way, distorted in any way, it's called an artifact because it's just like simply not an accurate representation of your body. And so in this example here, this commonly happens, refraction artifact, which is artifact associated with refraction, which is artifact associated with a bend in transmission is often seen around the pancreas and the aorta in transverse. So if you see this liver, okay, and then you see here's the panc, right? Liver, panc, and then you see this doubling of the aorta and then, like these other ones, but this is all normal. It's the doubling of the aorta in transverse. This is a common place we see this artifact, okay? So just kind of be mindful of that. Okay, so I'm going to wrap this video up with a brief overview of contrast agents and if there are any more videos available for review of chapter 2, please make sure that you are able to review those as well. Sometimes just playing this in the background and, going about your day, which sounds like a nightmare to have to listen to my voice like that, and I apologize, but it really does help you just get more familiar with the words I'm using, the different ways I explain it, and you're just going to be more and more comfortable hearing it, and then you're going to eventually be more comfortable speaking it yourself, which is a beautiful thing, right? Because then you're learning physics. So contrast agents are a type of solution that is administered to a patient, either orally or injected through the veins, so intravenously. And what it is, this solution is made up of gas bubbles. These gas bubbles are a special type of bubble. So the gas has a shell around it. This shell is made out of protein, lipid, or polymer, and it's made out of these small molecule shells. Okay. The protein molecules, the lipid molecules, or the polymer are very small, as you can see by this light pink. The gas the gas molecules inside of the shell are actually really big molecules of gas, and it's designed the gas bubble is designed like this with a purpose. They want the big molecules on the inside of the small ones because it's really hard for those big gas bubbles to push their way through these teeny tiny tightly packed molecules. And so eventually this shell will break down and these gas bubbles will disperse and eventually go away. We don't see them anymore. However, because of this design, because of the shell and because of this design, and as you could see here, they say that they use low solubility gas, or it's also described as being slow diffusion gas, which just means the gas slowly diffuses back into back into your, bloodstream. And so we want it to be like that because once this contrast is given to the patient, we want these gas bubbles to last long enough in your body so that we have time to go and do your ultrasound, right? And so if you can imagine if contrast only lasted a few minutes, we just wouldn't have enough time to get our work done. So why are we giving the patient contrast anyway? Well, we're giving the patient contrast because the contrast helps us see things better. It helps us detect lesions better. It helps us identify borders better, border detection, lesion detection. It helps us determine blood flow better. So I want you to think of the times in the lab when you have had a challenging time getting blood flow. So you were probably having a challenging time because you were scanning small vessels, deep vessels, or slow moving blood vessels, right? Slow, small, deep. And so those are the challenges that we face in the lab, right? Well, if the patient was administered contrast agents, they make flow characterization. So identifying if it's like venous or arterial flow. In your book, they say arterial and portal phases, which is he's just saying like venous and arterial flow. It helps ultrasound, it helps the sonographer, it helps the radiologist see borders better, lesions better, the flow within the lesions better, the venous and arterial flow in the case of a challenge, right? So if your patient's like very easy to scan, you wouldn't need to use harmonics. I'm sorry, contrast harmonics, which is an AKA for contrast agents. Okay, so this is actually your second type of harmonics that is taught in this book. The first one was tissue harmonics, and now we're talking about contrast harmonics or contrast agents, which that's just an AKA. So here's an example of how the contrast filled in this portal vein, right? So normally this portal vein would be anechoic, okay? And when echoes are placed in a normally anechoic region, we call that opacify. So if we're looking at something that was normally anechoic on ultrasound and now it's filled in with echoes, or now it has become echoic, we call it opacify. And that is what contrast agents do. They opacify. They make the image brighter. They enhance. Okay. So why do they do that, right? We understand why we would give it to the patient, right? The challenges in the lab that we may experience. We understand what the screen will look like. It will be brighter, more enhanced, opacified, more echogenic. Okay. So how do the contrast agents work in the body? What do those bubbles actually do? So when you think about the bubbles, I want you to think of the bubble having two different functions, which are located here on the screen. So the bubble has two different functions, or it functions in two ways, I should say. Okay. So first off, the bubble is, let me do this right. The bubble enters your bloodstream, right? So here we have, I still did it wrong. Hold on, hold on. Okay, here's the bloodstream. Okay, so here's the blood, and that is liquid. Okay, and then here's the gas bubble, right? When we compare the impedance or the resistance of the fluid in comparison to the bubble, the gas, they have, guess what? They have vastly different impedances. And when we say vastly different impedances, we know that that causes a very large reflection and a small transmission. So if the reflection is bigger, I want you to think about all of those echoes being going rushing back to the transducer, right? Like there's far more echoes being reflected back because the reflection is bigger. And so now you have all these echoes reflecting back. Those echoes are going to be turned into dots and eventually into scan lines, data lines, or a line of echo information. And then we know that we're going to have our ultrasound picture from that. And that's what makes our image look more echoic, right? More echoes, more dots. And so that's one way that the bubble functions, merely for the fact that simply for the fact that there is vastly different impedances between the liquid and the bubble. Okay. The second way that it functions is I want you to think of like what that bubble does when it comes in contact with the sound wave. So once this bubble comes in contact with the sound wave, so here's the sound wave, right? That bubble is going to start behaving in a very non-linear pattern, in a non-linear behavior. And so, what does that actually mean for a bubble? What is it going to actually do? Well, when the bubble starts behaving non-linearly or like not consistently, right? Maybe a little odd. What that really refers to is how the bubble is going to expand and contract. It actually expands in a manner that is greater than how it contracts. So it expands twice, right? Expand, expand, and it contracts. Expands, expands, and then it contracts. And so because it's not consistent with like, just like the basic expand, contract, and it's like a little bit more different and inconsistent, that is described as having a non-linear behavior. And I want you to think back at, what was the idea between the nonlinear behavior that I mentioned earlier. Nonlinear behavior was connected to harmonics, right? Earlier to tissue harmonics. Well, The bubbles, nonlinear behavior in this case, right? The contrast agents, nonlinear behavior when it comes in contact with the sound wave of expanding to a greater degree than it contracts, is also connected to harmonics. So harmonics once again doubles that room fee or that original frequency. So then it does have a positive effect on the image, which like only makes sense. Like, why would we even give the patient contrast harmonics? I'm sorry, give the patient contrast harmonics if like it's not going to have a positive effect on the image. But remember, it's going to double the original frequency. Anytime the frequency doubles, that means greater spatial resolution, more detail on your image. Aside from what I've mentioned, and there's more details in the book that you should read, definitely. But contrast has to also adapt to, these requirements. It has to be non-toxic, easily administrated, stable, so it has to last enough for sufficient exam time. You got to have that time to be able to go in there and do the ultrasound, and they have to be small enough to pass through capillaries. And that last one doesn't make perfect sense to me, but I just want you to remember that it does make your image more echogenic. It enhances the image, it brightens the image, um, and it makes it more echoic or it opacifies, okay? Aside from that, I have these charts that I recommend you either, I don't know if you can somehow take it from the PowerPoint here and add it to your notes and then fill it out as you go as a practice. But this is a good way to just kind of review information that you've learned in the past about chapter 2. And so I hope you enjoyed today's video and I hope that you get a lot out of it. Please let me know if you have any questions and have a good rest of your day.